section 5.6, we're going to talk about the fundamental theorem of calculus. It will begin 2 days of our adventure into the FTC. FTC stands for Fundamental Theorem of Calculus. Today will be part 1. We'll talk about part 2 on the next video. So far in this unit, you've seen an integral as a representation of area, and you've also seen it as a representation of an antiderivative. What we'd like to do in this section is bridge those two worlds together and show you how they're connected. In this first part here, I have several integrals to evaluate in the only way you know how, which is to find the area. The first thing I'm going to do is graph 2x, so y equals 2x. That's the integrand for all of these. And what's going to be different about them is just the limits that appear in each one. So they all start at 0, and the upper limit changes. On this first integral, because I see my limits go from a 0 to a 0, I know that no area has been generated, so my answer is just going to be 0. In the next one, my limits are now going to go from 0 to 1. So I'm going to look at my graph of y equals 2x that I have graphed and block off the limits from 0 to 1. It creates this triangle, and I know an integral is just area, so I'm going to find the area of that triangle. It's got a base of 1. Its height is 2, and I know for sure that the height is 2 because when I take a 1 and I substitute it into y equals 2x, I get a 2. And that gives me an area of 1, so the value of that integral is 1. Also, I'm going to keep track of these areas in this table, and we're going to look at this after we're done finding all of these integrals. In the next one, my limits are now going from 0 to 2, so I'm going to expand my area to go all the way out to 2. Now my area is 1/2 times a base of 2 and a height of 4, which gives me an area of 4, so the value of that integral is also 4. The next integral takes my limits from 0 to 3. The triangle has a base of 3, a height of 6, an area of 9, and therefore that integral value will just be a 9. Our last integral is going to take that upper limit to a 4. This triangle will have a base of 4, a height of 8, an area of half of 4 is 2 times 8 is 16. My integral value is a 16. What I like to do now is take a look at these areas and how they were connected to that upper limit and see if I see a pattern emerging. And what I see is the area that I got is whatever that upper limit was squared. So this first one, if I take 0 squared, I get the 0. If I take 1 squared, if I take this 1 squared, I get 1. If I take 2 squared, I get the 4. 3 squared is the 9, and the 4 squared is the 16. So if my upper limit is x, the area can be found by just doing x squared. So what's so magical about this x squared? If you look at its connection to the integrand on all of these, you can see that it is just the antiderivative. The antiderivative of 2x is x squared because the derivative of x squared is 2x. And that is the basis for this fundamental theorem of calculus. And it ties together how you can use that antiderivative to find the area. And as you'll see, it's far superior to what we've done in the past, because in the past we've either been reliant on our region to be a geometric shape, for which I could find an area formula for, or we were just finding estimates using those Riemann sums, but they were just approximations, not exact area values. You'll see in this will give us exactly what that area is, and I'm not dependent upon an area formula to find it. So if you're given an integral of f prime dx along the interval from a to b, you first find the antiderivative. So the antiderivative of f prime is simply f of x. Just keep in mind that was that question that would go through your mind. F prime is the derivative of what? And what answers that is f. Just notation-wise, what happens is our integral symbol goes away. Notice it is not appearing in this step right here. It's replaced by a vertical line at the end, and whatever your limits were, in this case a to b, they just go at either end. This is actually the way you say we're going to evaluate f of x along the interval from a to b, and then we sub in the upper limit. So you take your b and you plug it into your antiderivative, and then you subtract, and then you find f of a, so you substitute in your lower limit. In our first example here, We're just going to go ahead and look at the problem we did up top. And notice it's the same one that is up here. We already know the answer is 16. We did it using that area method. But let's go ahead and do it using the fundamental theorem of calculus so you can see how that works. The first thing I'm going to do is find the antiderivative of 2x. It is a power function, so I'm going to add 1 to the power. So it goes from a first power to a second power, and divide by that new power. When you learned antiderivatives, there was a big emphasis on don't forget to write plus c. I'm going to go ahead and write it. It's going to bring us to what I'm saying in this note over here, but for right now, we'll be consistent with what we said before, and we're going to write plus c. Notice my symbol, my notation has changed, so I don't have the integral sign anymore. I don't have the dx anymore. That is replaced with a vertical bar with a 0 to 4 at either end. So far I'm sitting at this step right here. I found my antiderivative and I've put my limits to the end. My 2's here are just going to wipe each other out. And now I plug in my upper limit. So I'm going to take the 4 and replace the x with it. And then I subtract this antiderivative evaluated at that lower limit. In the next step, I'm going to distribute this subtraction sign, and notice what that does to the c values. So my plus c minus c just zeroes out, and that 0 of course is just 0, and that gives me an answer of 16, which matches what I got above by doing the area. What happened here with these c values, about 1 being positive, 1 being negative, will happen every single time. So for that reason, there's no need to write a plus c if you have a definite integral. If you have an integral that has limits, then you do not need to write the plus c. When I did this antiderivative, I didn't actually need to write that plus c. I just wanted to show you why we don't need to write it. It's because it's going to zero out every single time. That's the basic process. Let's take a look at a few more examples. Example number 2, it's a definite integral, 0 to 6 of x plus 3 dx. My first move is to find the antiderivative. I'm going to take these limits and shift them to the end. This was just add 1 to the power, divide by the new power. Antiderivative of 3 is the 3x. And my 0 to 6 comes here at the end. The next thing I do is evaluate. I'm going to take the 6, plug it in for each one of these x's, and then subtract my antiderivative evaluated at the lower limit. Normally you wouldn't have to write the zeros here, but I just didn't want you to lose track of the fact that you have to plug in that lower limit. From here I just evaluate. This is going to be 18 plus 18 and give me a final answer of 36. Let's take a look at the next one. It involves a little bit of trig here. Again, my first move is just to find an antiderivative. An antiderivative of sine x is negative cosine x. Watch that negative. It's a common mistake for people to miss it. The derivative of cosine x is negative sine. Along with that negative is why it's positive over here. My antiderivative of 1 is just a plus x. My limits shift to the end, and now I'm ready to substitute in my upper limit. Here is the pi going in for the x's minus, and then I plug in my lower limit here. Just some small things to pay attention to. Notice I didn't write a plus c on this because I didn't need to, because I had limits on my original problem. And also notice how I encased these binomials in parentheses. It's especially important for this second one because you're going to want to make sure the subtraction sign hits each term if you have multiple terms in the second part over here. All I have left now is to evaluate. I have to evaluate what cosine pi is and cosine 0. The value of cosine pi is this negative 1, and the value of cosine 0 is a positive 1. And just evaluating things, my back-to-back negatives go positive, and I simplify and I get an answer of 2 plus pi. On to question number 4. The process is going to be all the same. What's different in these problems is just that integrand that you're starting with, which affects how you do that antiderivative. On question number 4, I have the square root of x. The first thing I'm going to have to do is a rewrite. The square root of x is just x to the 1/2 power. Notice when I did this rewrite, I kept the entire integral expression. I kept my limits here. I kept my dx at the end. Don't make those disappear until you do your antiderivative, which is going to happen in the next step. Power rule comes next. I'm going to add 1 to the power and divide by the new power. Same process and notation I did before. That leaves me here. My limits shift to the n, the one on the bottom, the 4 on top. I can simplify this a little bit. Dividing by 3/2 is the same as multiplying by 2/3. I'm now ready to do my substitutions, starting with the 4, and then subtracting the 1 being plugged in. This is your unsimplified answer. I'm going to go ahead and simplify a little more. Be able to handle these fractional exponents without a calculator. So this is 4 to the 3/2. That means take the square root of 4, which is 2, and then take 2 to the 3rd power. The value of this piece right here is going to be 8. This is a little nicer over here because 1 to any power is just going to give me 1 times that 2/3 is just going to leave the 2/3. And finishing these calculations out leaves me an answer of 14/3. In question number 5, again, my process is going to be the same. The only thing that's changed is that original function and how I handle that antiderivative. I'm going to have to do a rewrite of this 1 over x squared. Just like before, I'm not going to get rid of this integral and this dx until I do an antiderivative. In this stage, all I've done is a rewrite. I didn't need to rewrite this 1 over x because that is the derivative of natural law, and the power rule doesn't apply to that part. I'm ready to do my antiderivative, so I'm going to do my power rule here, add 1 to the power, divide by the new power. Here is my antiderivative, ready to be evaluated. Before I plug these numbers in, I'm going to simplify this part right here a little bit, handle that negative exponent. Now I'm ready to substitute in my limits, upper minus lower. Here is the 3 going into my antiderivative, minus. Here's my 2 going into the antiderivative. As we said before, it's especially important to remember to put parentheses around this back part so that that subtraction gets distributed through the parentheses and actually hits that natural log of 2 here. The rest of this is just simplifying. From this stage, I can take my negative 1/3 and my plus 1/2 and combine them together. And just be careful when it comes to simplifying this natural log part. If you have natural log of 3 minus natural log of 2, you might want to think it's natural log of 1, but it's not. You actually have to take the arguments for each one and you divide them when you have that subtraction sign. And this is my final simplified answer. If you are uncomfortable dealing with these natural logs and how to simplify them, it's actually okay for you to stop at this step. The requirement on the AP exam is for you to find and show an antiderivative, for you to plug the upper and lower values in, and if you want to stop at this step, that would get you full credit. Question number 6 has the exponential function in it. People tend to be scared of e to the x, but I hope to show you that in the calculus world, it's actually easier than some of the other things we do, because e to the x is its own derivative. It is its own antiderivative. So in this problem, when I do my antiderivative, which is the first step, I simply get e to the x evaluated along the interval from 3 to 5. Evaluating along those limits gives me e to the 5th minus e cubed. Just be careful you don't do an algebraic mistake and call that e squared, for the same reason you wouldn't take x to the 5th minus x cubed and call that x squared. So even though e is not a variable, you can treat it as if it were one. And one last example, because everybody loves trig. In this one, I first need to find what the antiderivative of cosecant x cotangent x is. What is going through your mind at this point is, this is the derivative of what? And the answer to that is negative cosecant x. Again, be careful of the negative and make sure it's there. My limits shift to the end. I'm going to plug in the pi over 2 first. Don't forget that cosecant is 1 over sine. So when you're looking at these cosecant values, you can write them in terms of the sine, and it might make it easier for you to evaluate. So it looks like this, and we know that sine of pi over 2 is a 1, and sine of pi over 6 is a 1/2. From here, this just becomes a negative 1, this becomes a 2, and negative 1 plus 2 is 1. As you see, the fundamental theorem allows us to evaluate a broader range of integrals. We're not dependent just on area formulas anymore, but we are dependent upon finding an antiderivative. So you want to make sure that you are good at those.